Welcome back to this course, Professional Scientific Communication. So, in this lecture today, we are going to look into an important question, that is, where do research ideas come from? Because these are, this particular topic is very important because how good your research is, how good your research question is, depends on what question you are asking or the idea that you sort of generated to address in your scientific project. Okay. So, the question is, where do research ideas come from? One obvious aspect of generating ideas is that you should explore your environment for ideas. It is everywhere, right? So, but you have to observe, you have to ask question. That is extremely important. The source of the ideas can be divided into two broad categories. One, that you do a literature survey, read about a given topic, and then you redo some of the experiments that people have done to see whether that can be validated if you have any doubt, and then you can extend the existing knowledge by adding few experiments, adding few more questions, therefore you contribute to the knowledge base. So, that is one that is very, very common, because research being too complex, in your stay as a graduate student, as a PhD student, or if you have taken up a 3-year, 4-year project, you will not be able to add substantially too much, because the complexity of the problem that you have taken. So, therefore, what you do is an incremental knowledge, you add to the existing knowledge by following what has been done before, what questions are not addressed and how to address them and why should I address them, and then how that may contribute to the advancement. So, that is what you do most often in a PhD or in a master's thesis. That is what we do. But at times we can also do something absolutely original. Nobody has asked these questions before. I have looked into and I have done this. This is far more challenging, but worth pursuing, because you are going to start altogether a new research topic, or you are going to come up with certain product that could be of great benefit to the society and so on. So, doing something original, though risky, is worth considering. Let us see how do you really go about asking these questions, and how do you generate ideas. You should ask questions. Questions are extremely important for scientific research ideas. You should ask, how does this work? Says who? Somebody said something, would you believe? You need to go and look at what is the reason that he or she said so, what experiment that person has done to say so. Was it based on certain principle? Was it based on certain observation? If it was just like that, then you shouldn't consider that. It is not that anything and everything that is written is correct. So, you need to question. I don't believe that. That is the way you test. You take it for granted, it's not going to work. So, you have to sometimes, if you cannot sort of go with the assumptions and the observations somebody made, you can redo the experiments and then see whether it is coming out the same way. Another important question is, why are we doing this? It's equally important, because just because somebody asks you to do something you shouldn't do, you have to ask question, is it really going to make any difference if I do this experiment? If the answer is yes, you should do. Why are they both right? There could be two different outcomes of an experiment, right? Somebody had done this, you have done this. So, both outcomes, you have used very similar approach, but the outcome is different. Then why? I mean, if it is science, then you need to ask question as to why both these observations could be right. So, you need to again look into that. Most often, at least in biomedical research, we learn a lot from abnormalities. Okay. So, if you look into, for example, any disease or a developmental disorder, all these are abnormalities. That is how you learn as to how things work. So, abnormalities really help. For example, you must have seen people with sixth finger. It is an abnormality. But we go out and look into the genes involved in that and identify the gene that is defective, which tells you now that this is the gene that is involved in, for example, the digits, formation of your hands, legs and so on. So that is an abnormality, that's what helps you. Again, rare conditions can give us an insight into how more common processes work. Often this is a notion that you are looking into something that is rare, which is not relevant, which is not the case. Most of the phenomenal discoveries that have been made in, for example, in biomedical research, have come from rare examples. The examples may be rare, but the outcome of that could address a more common processes. For example, people talk about Alzheimer's, Parkinson's and so on. These are dementia, and these are the disorders that affect the aged population. But do we know exactly what causes these conditions? This particular understanding, possibly this is the process that goes wrong, as a result you may have this condition, comes from some rare forms of genetic disorders which also result in symptoms which are very similar to more common forms of disorders. So the rare forms really help us. So the rare forms really help. So you should not neglect simply because they are rarer, therefore they need not have any relevance to the society. So these are some of the examples. So you need to ask questions, just don't go blindly by somebody saying that. You need to ask questions, you have to have discussions, and then sort of convince yourself that what he is saying is right, that I should do, or that what he is saying is not right, I should not do this, but I should do something else. So this is something that you need to take judgment. For this you really need to discuss, debate with people who have done that kind of research, because they have more experience. You may have a very good question and you probably may not get a solution because the problem is too complex and you don't have a tool to dissect that. So that is called practical, right? You can't really get into that problem because you don't have tools right now. So you have to wait for it. So who will tell that you cannot address this? Is somebody who has done that kind of a research. So it's important to discuss with people. So that is important, that you need to ask questions. That is extremely important in science. You should ask why, you should ask where, you should what if, why not, and so on. Ask questions. Don't just go by what people say. So if you look into the research career, for example, of a PhD student, this is something shown on the screen here. This was this is something that I borrowed from the slides of Kevin Byron. Is a very famous physicist in London, who has done phenomenal work not only in his chosen field, but about, for example, how to do research, how to innovate things. I mean, you should go and read about him and read about all his writings. It is absolutely phenomenal. Some of the ideas that I am going to discuss here today are all borrowed from his literature, papers, monographs that he has presented. So this is what he says, which anybody who has went through this process would know for sure is indeed the reality. So when you start your work, it's called as infancy. You have started your research career as a PhD student or for a master's thesis, and you have certain ideas. That is what is shown here in the green, in the lower bottom of left side, the graph. The green one, what is called infancy, is the germination of the ideas. You have discussed, you have read, and you have certain ideas. Then what you have is, then you have the idea and you ask questions, and then you have to answer these questions with certain approach. That's where you do experiments. Okay. So if you have very good hypotheses and questions and you have found appropriate tools to answer these questions, then you would get observations, and that is what called as rapid development. So you're getting data, right? It could be anything, right, for depending on what kind of approach you have taken. So you will be getting, but the tools and approach that you have used can take you only to certain distance. Soon you will find that you cannot go beyond that, meaning that you are able to address few questions, but still by then with the observations, now you have too many more questions which your data cannot address. So that's what called as competing theories. Now by now you have have the idea, observations, then you are interpreting the observations and you are getting that, okay, this could be like this could be like this. You have multiple theories, hypotheses coming out. So then it slows down, research slows down. So what do you need to do? So you have 1 or 2, 3 hypotheses. For each one of it, now you have to have approaches to answer. You have to prioritize. This is my first, this is second, this is third, and then again do experiments, and then you will get data which takes you to the next level. So it's a repetitive process, as shown on the right side on the screen. You have creative steps, okay, which help you to develop tools to address some of your questions, observations that help you to support your hypothesis one way or the other, and then you generate knowledge. Once that is done, then there is a delay, because now for the next step again you need to ask, evolve another set of hypotheses or questions. There are alternate possibilities, test each one of them and see which is correct, and then again it takes you. So if you see that always there is a creative step, and there is a delay, because then you have to assimilate, understand, and then devise new tools and approaches, and there are setbacks. For example, you may have 3 different hypotheses which may be compelling, which may be attractive, but may not be accurate. A given hypothesis, when you test, it flops. Your results don't come the way it is expected. I will talk about hypothesis a little later. Then as a result, what? You are going back to square one. You have to come up with an alternate possibility, again devise experiments, do research, and then you see whether it is. So there is a delay. So that is how, but with time you progress, right? And that results in a scientific communication, paper or thesis or degree, whatever, right, or a product. So that is how science works. There is creative step, there is a delay, and there is setback. So setback is very, very common to research programs. There is nothing unexpected. So if you are facing challenges in your research, don't feel bad, because that is expected that you would face setback, because only then you open some other door that you never thought about before, then you will find a way, right? So that is essential, and that's what being discussed in this particular chart. Let's see. So how, to be successful as a researcher, you have to be creative. You simply cannot follow the crowd. What is shown here is that there are some people who are more adaptive, some people that are creative, some people stay where they are, right? Adaptive are those people, you find that there are tools available, use that, and you get certain observations. But then you are good as the tool, right? If you don't have any tool, then you are not going to do, because the tools is not something that you are going to create. Therefore you have to be creative. Creative is somebody who doesn't really look for any laid out path or a place somebody had gone before. You have to go to a place where nobody has gone before. That is what called as creative. So you have to develop tools, new ways of reaching your target. That is shown on the right side. For example, put a rope, climb up, go. There is nothing like laid out path. It is tough, but it's challenging, but you can reach heights that no one else has reached. So you have to be creative if you want to be successful researcher. So this is important. It is not just doing experiment, but you have to come up with novel ways of doing experiments, novel ways of developing methods, and that itself is a challenge, something that you need to think about, and therefore you can go to places that nobody has gone before. I gave an example that failures are part of very good discoveries and inventions, so on. I'll give one example, okay, that is called as successful failure. So what is shown in the screen is that a snap of the astronaut who have come back from the mission to the moon without succeeding. That is called as Apollo 13 mission. And I'm giving this example because to get an idea for a project will be realistic, you need to know what resources that you have and whether you could address that particular question with the resources you have. You have a good question, but you also thought about the approach, but you don't have any tools with you, you don't have any resource with you, it's not going to help you, because you can do things only with what you have. So that is called as being realistic, okay. This Apollo 13, although it is called as failure because they could not, because this mission was to land people on moon and they could not do that, they came back, and still it is called a successful failure because they were able to do something unthinkable, to bring back these people who are on the mission, right. For this you need to go and watch this movie, Apollo 13. It is a 1995 Hollywood movie, and it is freely available. Those people who watch the YouTube, you can go and watch this. It's an excellent movie. So basically these are the 3 astronauts that are shown, the real astronauts on the left side, acted by people that are shown on the right side. They really wanted to go to the moon, and they were on the space mission. Somewhere when they were approaching the moon, their spacecraft developed some snag, and they had to really now find way not to land on moon, but to get back to the earth, because it is going to be challenging for them to come back. So the mission now, the whole mandate of the mission has changed, not for landing on moon, but to get back, to fix the problem that the spacecraft has developed, and to bring these people back to the earth. And this cannot be done by people who are sitting in the mission control room, who are in our planet, but by people who are in the spacecraft, the 3 astronauts. Not only that, they have to do with whatever little that they have in the spacecraft to bring them back. Therefore, you have to innovate. You have to do things very different by having only those few things that you have at your disposal. And you can do that if you have the limitations, right? So you need to know the boundary. So these are the things that I have. This is the question I ask. Can I do this? The answer is, if you know what you have, and if you can do that, that's best. You cannot really think of something that you don't have and say that, oh, well, I couldn't do. That doesn't help. So you need to see what you have and how that could be addressed. That's where, that movie really helps you to understand, and why it is called a successful failure, because they could not land on moon, but yet they could come back. Therefore, it is successful failure. I'll give you some other example as to how sometimes a simple observation, simple approach can make great impact in science. This is about a famous scientist called Susumu Ono. Sort of put the hypothesis, and he tested the hypothesis to some extent. He has proven that the mammals, all the species that we are one among them, they're called mammals, have pretty much the same amount of DNA per cell, and that the X chromosome, one of the chromosomes that we have in our cell, is about 6% of the total DNA. This is something he said even before we know how much DNA per cell we do have. So this was done in 60s when nothing was known about, but he used very simple approach, and this is called as Ono's law, because now we know that it is absolute. What he said is correct, accurate, therefore it is called law. So how did he do that? If you look into the mammalian species, there are species that have only 6 chromosomes, like the one that is shown on the left side. It's one of the deer family animal which has got only 6 chromosomes, and there are animals that have got a large number of chromosomes running up to 60 pairs, 70 pairs, 80 pairs, and so on. But what he did was remarkable. So he made this kind of what is called as chromosome preparations, and took a photograph and then printed them in the same magnification using the printing papers. People used to do that kind of printing earlier, and then you cut each chromosome with the scissors and you weighed. You find that regardless any species that he looked at for the chromosome preparation, regardless of the number of chromosome, the weight of the chromosome cutouts were identical, and the X chromosome was about 6% of the total weight. Therefore, he said that the DNA content per cell in all the mammalian species is constant, and sex chromosome is conserved, meaning the genes that are there in X chromosome are identical possibly in all the mammalian species, and that constitutes 6% of it. It is a remarkable discovery. Now we know with the advanced techniques, where now we have sequenced the genome, and each chromosome sequence is known, number of genes known, the length of the DNA known. Now we know that what he said is accurate. Therefore, we say it is Ono's law, because that is something that we can prove now, which he has proven about 60 years back with simple approach, right? Just photography, cutting the chromosome, weighing using a balance that is the physical balance that you must have seen in chemistry labs. So that is what science is. You have to have observations, you have to have good questions, and then look at tools that you have which can address, and then you can come up with discoveries that are time tested, and now we call as laws. So it is doable, right? So why some are successful? Because they're able to ask questions, right? This is what something that is put on the screen. Again, they borrowed from Kevin. That is, I have 6 honest serving men they taught me all I knew. That's what he confessed. I call them what and where and when and how and why and who, because these are the questions that you ask to address any problem and then able to come up with something novel discovery and so on. So if you look into the questions, the question that you ask is fundamental to research. Okay, it's called as the inquiry wheel. Again, I'm borrowing it from Kevin. These questions really, ask, like you ask something and then you start observing. That is called as observing, right? Once you observe, again you ask certain questions that these are patterns that are similar, these are patterns that are similar, and then you define a problem. Okay, when these patterns exist like this, probably they mean this. Okay, and then you ask again question, or is it that you have a pattern that the animal behave in a different way? That's the question you ask, and then you test them, right? And then when you test, you know that what question you asked is accurate, then you say that yes, that's what's happening, and then you go on, addressing each one of it, and finally, discoveries are made, you communicate, others get to know, and this is called as the inquiry wheel. All great scientists that you talk about, whether it's Darwin, Mendel, all these people have asked these questions, right? That's why even after centuries of their discoveries, we still talk about. For example, you call Mendelian laws, you call them laws because every gene that you talk about that form that kind of segregation obey whatever Mendel expected, right? That's why it's called the law, right? But these were observations, these were theories, these were hypotheses, but many scientists have repeated these experiments, and you can predict that this would happen and it would happen. That's why it's called as law, right? Therefore, asking question is an important integral part of science, and you need to question. At every stage you need to question. Without question, you will not get an answer. When I say question, it's not that you go and question somebody else, right? You have to ask questions, to yourself, to your own, scientific problem, and then find an answer for this. It is you, by reading, by thinking, by discussing. It's not that somebody is going to come and give you a solution. That doesn't happen, right? Therefore, you need to ask questions. So let's revisit the 6 honest serving men who could help me in finding ideas. From where do you get idea, right? Why, what, where, when, how, and so on. So you can see everywhere. For example, there are campus, like you go to your university or you go to institute, you spread out, there are so many buildings. You want to meet a particular faculty in a particular department. What do? You need to ask if there is a security person, there is a guard, or somebody. You go and ask, okay, this is the department I wish to go, this is the lab I wish to go, this is a building I wish to go, where it is, right? What if nobody there? How will you find? It becomes challenging. Therefore, there are signboards like what is shown on the left side. It says you have to go this way. For example, you go to a park, then it all says that. It's easy, then you don't need to ask anybody, right? But at times, you may have campuses which have roads, which have buildings, nothing is named, no signage. Then you have to go and ask, somebody there as to where it is. Now, whether he would help you depends on whether he knows where that particular building exists, where the particular department exists, or his information may not be accurate. He would say, you go on the right side, turn left, there is a tall building, that's where the department is. You may go there, you will find out it's not that building, right? Therefore, it becomes challenging. So you can simply ask a question, how can I change this environment? Can I make, for example, very good signboards? If I were to do that, what would I do? How will I do? What are the things that I need? What information I need? Who should I contact? How do I make effective signage boards? It is a simple example for you to work out in your own college, in your own institute, in your own university, in your own township, how possibly you can make a difference. This is what ideas, right? You can make the difference, right? That's what it is. Define the problem. The problem is you don't have signages, or there is a problem because you don't have very good way of communicating, or it could be there are people from who speak different language, they come here, so putting one language may not help. So you want to have something very different than what others thought about. The need could be different. Therefore, you need to define the problem, and then you have to ask questions as to how to address the problem, and then who should be approached if you want to implement. So in all these, you ask questions. And it is everyday our part of life that you go to railway stand or bus stop, then you will find that bicycle parked like this. You left your bicycle in the morning, you come back, you want to locate your bicycle, it's going to be extremely difficult to pull out your bicycle. So can there be effective way when in the crowd of hundreds of bicycles that are there, how can I locate anyone's bicycle? Is there a way I can improve the system? Or for example, a junction, a road where 4 different roads meet together in any of the Indian cities, it's a chaos, right? You don't really find a way. Can this be addressed? Most of the developed societies have addressed this problem and they do follow, right? But maybe that is not practical here, or maybe you don't follow. But you can ask questions how this can be answered. Whether you're able to do it or not is different, but asking questions, finding a solution will improve your curiosity and your ability to come up with certain solution, which who never knows. One day you may become the mayor of that town, or you will become an administrative officer, or you could become a politician who could possibly fix this issue. So you have to think about it and ask questions and think about solutions which would help you to become a better scientist. So that is what it is. So you have to look for ideas. These are either that are there in the literature you read, and then you find what is not present, what is the black hole, what is the point that is not discussed, and then do experiment to add on to the existing knowledge or do something altogether original. And then for all these things you need to ask questions. Okay, so I'll leave you with certain contemporary topics for you to discuss, think about, and ask questions and approaches. One is, for example, often that is there in the news now is Delhi pollution. The pollution level, this is the most highly polluted city in the world, right? And then there are doctors who say that, well, get out of this city, this is not good for your health, you may have all problems, right? So that's what it is. So now the question is that why Delhi is having very high level of pollution as compared to other cities? Is it the problem that has a source in Delhi itself or something else? This is one question that you may want to address, because without knowing the genesis as to why you have pollution, you cannot solve it. So once you know why do you have pollution, then you have to come up with ways to mitigate, to control, to reduce, right? So you need to ask questions, you need to go and investigate. Most of this can be done by doing literature survey. That is what I want you to do. Go and read, and you will be able to find. But you have to ask questions. Even if you want to go and search it in the Google, then you can get an answer only if you are able to type a question, right? So therefore the questioning anything is important. Even to get an answer for a question that is already there, you need to phrase the question and you can get it. So you practice using Google search or Yahoo search, but you need to have questions. So when you ask questions, probably you get an answer, then you can make a small report that would help maybe as a school project or as a college project and so on. But you need to know first, what is the source of pollution? Why Delhi? What is unique about it? How are you going to mitigate? How long it will take, right? When these are the elements that you would get answer only if you ask relevant questions. There could be other. For example, some time back there was a lot of buzz about the superbug named after New Delhi, because somebody who came to Delhi had this particular bug. Therefore, they said that the bug exists in India, and there were a lot of research, which papers and so on, which said probably is not something new or not from Delhi or things like that. So you want to ask the question, because you don't want to have your national capital named after a bug which is not so good, right? If it is named after something which is good, it sort of gives a positive image. So you want to see whether really is it from here. So you investigate again, you may get very good answers for that. Now you can go for even contemporary problem. So there are newspaper reports which say that the demonetization which happened about 1 year from today led to job loss, for example. It really killed the small scale industries and people who run small shops and so on, which may be right, which may be wrong. but how will you, say that is correct or it did not affect or did affect? You have to, go and analyze. How do you do that? There are ways to do. There are growth indicators. You have to go and survey people, look at their profit ratio, and then come up with a report which suggests yes, it did affect or it did not affect, because you cannot just follow something what people said, because there could be sampling error, right? They would have taken only, for example, one particular city which has got so many travelers, tourists, and they were dependent on the tourists when demonetization took place. For example, only those industries that were dependent on tourists, were affected. But if you go to something else, which sells, for example, day to day bread and milk and so on, I have money when there's a demonetization. I'm not going to spend on visiting my relatives, but I would spend my money in buying essential needs. Therefore, this particular market, right, or the shops may not be affected. So therefore, you cannot make a sweeping statement. So you have to ask questions and methods to validate and go and find yourself whether it really had an impact. Another biology-centric problem I can suggest is that, for example, all of you must have known about this gentleman, Michael Phelps. He is one who has a record for winning the maximum number of gold medals in Olympics, right? He's a swimmer from Australia. This guy, he is phenomenal. If you look into the records, you may want to go and check. And one of the suggestions or hypothesis was that this guy has got the lung surface was so huge than many other swimmers. This guy is able to, inhale a large volume of air. Therefore, he could get more oxygen than most of the people. Therefore, he is able to power himself better as compared to other swimmers. This may be just, a kind of a notion that may not, survive the scientific scrutiny, or it could be, just a coincidence that he has got a larger lung surface, but really that alone did not make him a different. So how will you test it? So you have to ask questions. Is it that every swimmer who is successful is able to get, win a gold medal in Olympic has got large lung size? In other words, is it that anyone who has got large lung surface excel well in athletics? These are the questions that you need to ask. When you ask, then you will find an answer which really come up with certain discoveries that could be become a kind of in future what is called as law. So these are the ideas. That is something that you need to look, and then you can take up and then go and sort of build on. And that's where I leave today for in this lecture, that you have to look at your surroundings, your environment, ask questions, right? And then go on, when you ask questions, you can seek answer. You yourself go and read about it, build and write a small report on, for example, the Delhi air pollution, or on the superbug, or on Michael Phelps, or on demonetization. You can go and do a survey, and you can, with your own small town, you can come up with certain conclusion as to whether really it had an effect and so on. So that is how you sort of develop first your curiosity to observe, curiosity to ask question, curiosity to develop an hypothesis, curiosity to test the hypothesis and come up with conclusion. So you have to keep your eyes open, you have to look at patterns, you have to sort of think about it yourself and ask questions and find answers, which eventually would make you a successful researcher years to come. So with that, we will end this particular lecture, and we will meet again for the next lecture, where I'm going to introduce to you what is called as hypothesis building. See you again.